Well, here we are once again. It's the physics video lecture. Physics 105B video lecture 35. So we're talking about Hamiltonian mechanics. This is a great subject. I'm going to warn you, or just give you a heads up, it's mostly formalism now. We're not going to solve any new problems, but we're going to get a lot of insight. And this is essential for understanding quantum mechanics, or for working in quantum mechanics later on. So it's a great subject. Let's just jump right back into it. We start with Lagrangians. So I'm going to go ahead and do a step-by-step list of what we have to do to make it into Hamiltonian mechanics. We start with, just make one of my lists, right? We start with a mechanical system, and we need a set of coordinates, their derivatives, their first derivatives. We know that P sub I is dL dq sub I, and we need Lagrangian. So continuing this thought here, where L is equal to L of Q1 to Qn, Q1 dot, Qn dot, and T. So yeah, we need a Lagrangian system, and we need its, we have its equation of motion. In particular, though, this generalized momentum plays a role, because we want to go from Lagrange to Hamilton. So once we've constructed this, then I'm going to write it this way. We start with the energy, EL dqi dot, which is P sub I, qi dot minus L q dot T. That's not yet the Hamiltonian. Nor is this, right? We call that P sub I, Q sub I dot minus L. But yeah, we construct the energy, and then we, by means of essentially an algebraic transformation, we express this only in terms of coordinates, momenta, and time. In other words, it's not allowed, or there can be no Q dots in here at all. It really has to have been turned into Q, P, and T. And the really simple example is that if you have L equals a half mx dot squared minus u, you end up with H equals P squared over 2m plus u. Okay, so that's how that transformation goes. That's the example I worked with last time. So once you have this, then you have equations of motion, namely Q sub I dot is equal to partial H with respect to P sub I, P sub I dot equals, that's one dot, minus partial H with respect to Q sub I. And this second one turns into Newton's law in the simple appropriate cases. But these are the so-called Hamilton's equations, or the canonical equations. And the example I showed you, namely this simple one up here, when applied here, of course, these two first-order differential equations turn back into one second-order differential equation, which is Newton's law. But there are aspects of the whole theory where we stick with the two first-order differential equations. That's going to be really interesting. So right now, I'll just leave that there. And I'll give it a little note. like I said, this conversion here, this is the proto-Hamiltonian. When you've converted it here, then you really have it. Coordinates, momenta, and time. This transformation is an algebraic problem. This example was very trivial, and as long as each p here, as long as each momentum only depends on a single coordinate. Oops, got a mistake up there. All right. Let's repeat that. There's a dot right here. Okay. Okay, once more. As long as a momentum only depends on a single generalized velocity, the transformation is easy to do. Okay. It's basically as easy as what we just did up here. Now, principally, that doesn't have to be the case. L depends on all of the coordinates and the generalized momenta, and that partial derivative can principally depend on all those things as well. If that's the case, or if it depends on just even more than one, then you've got yourself an algebraic problem that will not deal, we won't bother with that. The examples we're going to do will be of the nature where just one momentum for one generalized velocity. But just to give you an example, the small oscillations problem with an off-diagonal M matrix would be the kind where you'd have to do some algebraic work to actually do this transformation. So maybe I should write that down, and then you guys can work on it a little more if you're interested. So transformation, which I'm going to call star. This is that transformation right here, okay? I'll get this thing here. Is essentially trivial. Going out on a limb calling it trivial when each piece of I only depends on one q sub I dot. Okay, so that's easy, and those are the ones we're going to do. I'll assign a couple more basic ones for you. So let's see. The example I wanted to give, let's go ahead and write it this way. Example when this is not the case. Okay, so that would have been, we had, say, L equals 1/2. Okay, here's a good one. M11 x1 dot squared plus 1/2 M12 x1 dot x2 dot 1/2 M21 x2 dot x1 dot M22 x2 dot squared, and minus u of x. We'll write it that way. Don't want to write out the rest of them. So what we're looking at is the kinetic energy part of a small oscillations problem where the M matrix is not diagonal. Okay, so we've even done a couple of these, so we know that's a real thing. Now let's go ahead and do this P. Since we have two coordinates, we're going to have two momenta. So what's P sub 1? It's dl dx1 dot, right? And that would be M11 x1 dot, and that term there, and then plus 1/2 m12, differentiate the x1 dot, x2 dot plus 1/2 m21, m21 x2 dot. And that simplifies a bit, but only so much. So that's m11 x1 dot plus, and remember, we can always have these things be diagonal, so we'll just say symmetric. We can always have the M matrix be symmetric, so we have m12 x2 dot. Okay. So now you have P1 depends on x1 dot and x2 dot, and you're going to have to do a little linear algebra to turn this thing into a Hamiltonian, and we're not going to do it, but I just wanted to point that out. So we could say this is an off-diagonal example. And it's from small oscillations. You know, you could write the half k ij squared as well. Okay. Yeah, if you were to do p sub 2, you'd have something similar here, and you'll have two linear equations, and you can then express x1 dot in terms of p1 and p2, okay? And you go in there and get the Hamiltonian. So that's enough. I should write a couple words so that you have them here. If you wanted to do that, you could, but we don't need to, we don't want to. We already solved these problems with the Lagrangian method, right? The problem with small oscillations. Yeah. So note that x1 dot is then going to be x1 dot depending on p1 and p2. So it can be inverted, it just takes a little more work, etc. Okay. So good, we're back to finding a Hamiltonian, getting it into, you know, this form here, and then we have the canonical equations. So I will next ask for a couple of easy examples. I'll put them on as a homework so that you guys can think about them and do them. Leave some space in your notes. Possibly you can just write them down. So, homework. We already had the Hamiltonian for the central force problem. And we're going to return to that, by the way, but let's just say construct Hamiltonian for point mass in Cartesian coordinates. You know, pretty trivial, but and a point mass in cylindrical coordinates. We already have it for plane polar coordinates, like I said before, because it was a central force problem. So yeah, the Cartesian coordinates, you just have 3 p squareds, x, y, and z. And cylindrical coordinates, you take your plane polar coordinates and add that other coordinate, the z coordinate. Okay, so that, like I said, you just leave the room in your notes and fill that in. But what we want to move on to is, what's the best order here? Talk about cyclic coordinates. Actually, before I talk about cyclic coordinates, I'll put here number 3 under the homework. This is the important one. These two are kind of trivial. this one here is very important. We want to find the Hamiltonian for a particle in an electromagnetic field. And for that, we actually need the Lagrangian. So this one is the important one. Particle in electromagnetic field. And as you'll recall, we had the Lagrangian already for the particle in the electromagnetic field, and we want to get the Hamiltonian. So we have L equals 1/2 mv squared minus q phi plus q a dot v, right? V dot a dot v. Q a dot v. And so we did this one before, and remember the assignment we did, hope we did this one, was to show that the Euler-Lagrange equations for this give us the electric and magnetic forces on a point particle. So I'm gonna repeat all that. So we have phi is equal to phi of x, y, and z, or x1, x2, x3. A, that's 3 components, the vector potential. Learn about that in Physics 107. A of x1, x2, x3. So you have A1, A2, and A3. And we know that the minus the gradient of phi gives us the electrical field. The curl of A gives us the magnetic field. Okay. And what we saw was the Euler-Lagrange equations for this. Euler-Lagrange equations tell us that m, I'll say vector x, second derivative, is equal to q e plus qv cross b, with all of these conventions right here, okay? So this was an important Lagrangian, and it's maybe even more important as a Hamiltonian, okay? And the reason is that this would be the Hamiltonian that's used for your basic and very important atomic physics applications. Because, say, in atomic physics, you solve the hydrogen atom and get all of its energy levels and other interesting features. And that uses the Hamiltonian formalism. But then you want to couple that hydrogen atom to an electromagnetic field and get the more detailed effects, the Stark effect and things like that, the Zeeman effect. And for that case, for that situation, you have to couple to a potential here, an electric and a magnetic field, and this is the way the coupling occurs, and this is the way the quantum mechanical formalism is going to have to start. But it's not going to be the Lagrangian, it's going to be the Hamiltonian. So the homework is to construct the Hamiltonian, and I'll get you started on it. If you have some time, or if you can find where you did this, you may run through this again to make sure you see that that is true. So we want to construct this Hamiltonian, and this is the one you'll see when you study atomic physics, okay? And when the classic problems of atomic physics are solved. Okay, so here's the particle electromagnetic field. So I'll add notes to what we have up here. V is equal to x1 dot, x2 dot, x3 dot, right? So we have L, if we would write this out, we have 1/2 m x1 dot squared x3 dot squared, okay, minus q phi of x1, x2, x3, long expression here, plus q A1 of x1, x2, x3 times x1 dot plus q a2. So if you write it out like this, you've got everything in front of you. That's why I'm doing that. You have all your arguments and everything, right? x3, a2 of that x2 dot plus q a3. You probably did it this way last time too, possibly. x3 dot, okay. Yeah, so you want to construct the Hamiltonian. So homework, right? Construct H, construct the Hamiltonian. We can already see you've got p sub 1 dl dx1 dot is going to be mx1 dot. Well, that's the ordinary linear momentum, but we also have x1 dot right here. So it's plus q a sub 1. I won't write down the arguments, okay? So that's p sub 1. So your x1 dot is equal to p sub 1 minus q a sub 1 divided by m, etc. I'm pretty much giving it all away, but that's all right. So when you go ahead and go back into the Hamiltonian with this, you know, into the energy and construct the Hamiltonian, and you're going to square this, just, let me do this. Leave it like this. There's no point in expanding this thing out. Okay, so you leave it in a simple form, and that's the form you'll see in the books, because of course this thing's been done 1,000 times. Okay, do not expand this expression because you'll just make it complicated. We don't need it expanded. Okay, so yeah, but that's how you do this one, and you'll get your Hamiltonian, you know, and then you'll have that in your book of golden results. And when you study quantum mechanics and atomic physics, then you'll know where that particular Hamiltonian comes from. I still remember I didn't know where it came from the first time I saw it, but you guys will know. Good. So there's that important problem. Let's see how we're doing time-wise. Excellent. So we've got that, and I wanted to talk about cyclic coordinates as well. So next topic is cyclic coordinates. So now we're going to assume we've gone through the whole rigmarole, starting with our Lagrangian, and we now have a Hamiltonian. So H equals H of Q1 to Qn, P1 to Pn, and T. Okay. But one of these coordinates is a cyclic coordinate. But let's say H is not explicitly a function of some Q sub K. So one of these between 1 and n is not explicitly present in the Hamiltonian. And similar, I mean, it's really the same as in the Lagrangian formalism. You've got all of your momenta, you're missing one of the coordinates. Just in Lagrangian, you have all of your generalized velocities, you're missing a coordinate, okay? So good, this is what I mean. So Q sub K is cyclic. Well, immediately we have P sub k dot, which is minus dh dq sub k, that's Hamilton's equation, one of them. Q sub k is cyclic, so that's identically equal to 0. And just as with the Lagrangian situation, P sub k is a constant. And I'm just going to name it alpha sub k, because it's no longer a dynamic variable. What this does is, so right now I'm going to say, yeah, right, explicitly the n variables in there. What this does is, it reduces the number of variables in the Hamiltonian. So, reduces the dynamical variables. Okay, let's write that. Reduces the dynamical variables in the Hamiltonian by 1. And for example, if we had h of q2 to qn, p1 to pn, right? So if q sub 1 had been cyclic, then this would be turned into h of q2, qn, p2 to pn, and then I could treat this conserved momentum as, I'll just call it alpha sub 1, as a parameter. It's now just a parameter in there. And the goal of mechanics then, if you continue on in this direction, is to find coordinate systems in which as many coordinates as possible are cyclic. And in fact, there's a formalism in which you can make all of the coordinates cyclic, but that requires, you never get anything for free. So if you get all the coordinates cyclic and all the momenta are conserved, then you have a whole formalism to do that, which we'll study in graduate classical mechanics. But the thing now, this is, you would think this is the same as the Lagrangian situation, and it is up to this point, but being able to plug your parameter back into the Hamiltonian is something new. And because you still have Hamilton's equations. If you try this trick, or if you try to do this with the Lagrangian, you're not allowed to plug the constant back into the Lagrangian. You'll get wrong equations of motion. So yeah, bottom line is cyclic coordinates, you have the same benefit, the same relation to symmetries that you had in conservation laws that you had in Lagrangian mechanics, but you can use it to reduce the number of variables systematically in your Hamiltonian. Okay, and actually I have an interesting problem for that. Maybe I'll have you do. Yeah, let's put a little homework problem. With this. And in fact, this is a nice extension of what we've been doing. So what we'll do is, we've already constructed the Hamiltonian for the, so one more homework problem which really builds on what we've done. Okay, we've constructed the Hamiltonian for the Lagrangian, central force Lagrangian. Okay. So here's what we want to do. Central force Lagrangian L equals 1/2 m r dot squared, r squared phi dot squared minus u of r. And we know that P sub phi equals m r squared phi dot is equal to constant, and we called it L, so angular momentum. just said central force. Now H equals H of R phi p sub R p sub phi. That was your homework. We know that it's not going to have phi explicitly. Therefore, we could say that H equals H of R piece of R, and I'll do a semicolon here, and that conserved angular momentum that we're naming alpha. Up here we're naming it L, down here we're naming it alpha. Okay. And we'll leave the U of R unspecified. Down here it's minus U of R, and the Hamiltonian is going to be plus U of R. Okay. So here's what we want to do. We want to compare the Euler-Lagrange equation and Hamilton's equations. So the homework is, 1, compare the Euler-Lagrange equation to Hamilton's equations. So carefully write them out. Okay. This is complete, by the way. If you have Hamilton's equations for this one variable and the definition of this alpha, which was the conserved angular momentum, right? So you want to compare the Euler-Lagrange equations. Now here's where it gets tricky, and I want you to be careful with this. What we want to do is construct a forbidden Lagrangian. L tilde is equal to L with m r squared p dot squared over 2. Okay, m r squared p dot squared over 2 replaced by L squared over 2mr squared. Okay. So the point is that the Euler-Lagrange equation for L tilde, where we made this replacement, which is the same replacement we're making up in the Hamiltonian, but if we make that replacement in the Lagrangian, it's going to give us a wrong differential equation. Show that Euler-Lagrange equations for, in fact, there will just be one. Okay, there will be one equation. L tilde is wrong. The right one you already have, so you'll see that it gives you a wrong answer, and it's pretty subtle because it looks really good, except it's off by a minus sign. So this feature here of reducing the number of dynamical variables is allowed with Hamilton mechanics, but not allowed with the Euler Lagrange equations, with the Lagrangian. And the reason is that in Hamiltonian mechanics, here we go, point at these. In Hamiltonian mechanics, all of these Q's and P's are independent dynamical variables. Okay, and the equation of motion came from a variational calculation that we did. In Lagrangian mechanics, the Q dots, so you have Lagrange, the Q dots are not independent of Q, okay? So here's what we do. You guys do this, and like I said, you're going to get an equation with a wrong sign in it somewhere. It's going to look just as good as another equation. And then I may come back to that again when we talk some more about the variation calculus. Okay, but for now we have a good set of a couple of easy problems to do, and we'll pick it up there next time. See you later.